For the rest of this week, we'll do a larger example on discrete event simulation. The central idea is that we will use mutable variables to simulate changing quantities in the real world. As a side effect, so to speak, you will also learn how to structure a system into a sequence of layers, and some of these layers will be domain-specific languages. Concretely, we will construct a digital circuit simulator, and that simulator itself is based on a general framework for discrete event simulation. Simulation and digital circuits by themselves could probably take up a complete course, but with the right tools at our disposal, we are going to see that we can simplify it enough to compress it into less than 1 hour. So let's get started. Let's start with a small description language for digital circuits. A digital circuit is composed of wires and functional components. The wires transport signals that are transformed by the components. Because we're dealing with digital circuits and not analog ones, we represent the signals simply using the booleans true and false. The base components are also called gates, and they are the inverter, whose output is the inverse of its input, the AND gate, that forms the conjunction of its two inputs, and the OR gate that forms the disjunction of its two inputs. From these basic components, we can construct others by combining them using wires to connect them. Another thing that's important is that the components have a reaction time, that's called delay. That means their outputs don't change immediately after a change to their inputs. There's a delay until that change takes place. Digital circuits are usually described by diagrams, and the basic components of these diagrams, the gates, they are drawn as follows. Let's start with the inverter. So the inverter is simply a triangle with a dot at the end that transforms its input here on the left-hand side to its output on the right-hand side. So it's called an inverter. The second basic gate is the AND gate. So that's written like this. It takes two inputs and transforms them, takes the conjunction of the two inputs in their output. So the output is true if both inputs are true. And finally, we have the OR gate, which takes two inputs and converts them to an output which is true if either of the two inputs is true. From these basic gates, we can now construct more interesting circuits. So we are going to show how to construct a half adder that takes two inputs and converts them into a sum and a carry. So let's take the two inputs, call them A and B. What we would do is we would form first the AND of the A and the B. That's written like this. And at the same time form the OR of the two inputs. That's written like this. And then we place an inverter after the AND. And finally another AND gate here. And that gives us the sum on this wire and the carry on this one. So if we do the math, then we will see that the sum is computed by taking the A or B. Then we have an AND here and not A and B. So the sum is set if either A and B are set and not both of them are set, whereas the carry is A and B. So if both A and B are set, then the carry is 1, but the sum is 0. If either A and B are set, then the sum is 1 and the carry is 0. So let's wrap this up, draw a box around it, and call it a half adder, or I'm going to abbreviate that to HA. You've seen the circuit diagrams. What we're now after is a textual language that describes these circuits. So the idea is that we would have wires, and the wires are here named, so they have names. What we are going to do also is name the internal wires, so there would be a wire here and a wire here. And those wires we can create using a class wire. So we can create new wires by writing val A equals new wire, and then B equals new wire, C equals new wire. That would create the 3 new wires A, B, and C. Or equivalently, we can abbreviate that to just writing val A, B, C equals new wire. And that way we can create all the wires in our circuit diagram that you see here. And finally, we can place the gates between the wires. So one thing that's important here is that a wire is not just a single straight line, but everything that's connected until it hits a gate. So the B wire, for instance, would consist of this line, but also this line here. But not that line here, because there's the OR gate between that line and that line. So that's why we have renamed that wire to be D and that wire to E. So once we have wires, we still need to place the gates. And that we do with the following functions. We have an inverter function that takes as inputs 2 wires, the input and output wire, and places, so to speak, the inverter as a side effect onto the circuit board. And the AND gate would do the same thing. It gets 2 inputs, A1 and A2, and an output, places the AND gate between those wires, and the OR gate analogously for 2 inputs and 1 output. So let's see how we would express our half adder using this language. So a half adder then is a circuit that takes 4 wires, the 2 inputs A and B, and the outputs S and C. What we need to create then is 2 internal wires, that's the D and the E, that's done here. And then we place an OR gate between A, B, and D, that's that gate here. We place the AND gate between A, B, and C, that's that gate here. We place the inverter between C and E, here you see it. And finally we place the AND gate between D, E, and S. And that together, wrapped up, gives us a component which we call a half adder, which is its own function and therefore can be used as another component, just in the same way we can use OR gates, AND gates, and inverters. So we can use that, the half adder, then to place between input and output wires. So here you see a full adder that can be constructed from 2 half adders and an OR gate. To understand that, let's draw the diagram first. A full adder takes 3 inputs, the A and the B, and an input carry. And it works by placing a half adder between the B and the input carry. Then placing another half adder between the A and the sum of the first one. That sum result would give us the final sum. And as to the carries, we produce them by taking the OR of the 2 carries of the half adder. So here we get the sum, and here we get the output carry. Let's name the internal wires. So we would have the internal sum of the first half adder and the 2 carries, call them C, C1, and C2. So that would give us a full adder of 1 bit. Now to put that in text, you see the function here. Full adder takes the 3 inputs and the 2 outputs. There are 3 internal wires, S, C1, and C2. And there's a half adder between B, Cin, S, and C1. There's a half adder between A, the sum of the first one, S, sum, and C2, and an OR gate between C1, C2, and Cout. And now we have a full 1-bit adder, which in turn, of course, we could use to produce a 8-bit adder, 16-bit adder, or any other circuit you like. So here's an exercise for you. I have a mystery function, call it F, that connects 3 wires A and B, the way you see it here. And I want you to answer what logical function does this circuit produce on the output wire C. Is it A and not B, or A and not B and A, or maybe B and not A, or A equals B, or A not equals B, or A multiplied with B. So to figure out what this circuit computes, a good way to proceed is to look at the internal wires and see what logical function they would produce. So if we look at the F, for instance, so as it says, that would be the AND between the A and the E itself is the inverter of the B, so that would be AND A and not B. Likewise, the G would be B and not A. And then we have, as a final result, F or G. So that means that either A is true and B is false, or B is true and A is false, and that those are the two possibilities that turn the result true. So that means the result is true whenever A and B are different. So the right solution is this one here.